Alright, gang. Here we go. Woot woot, colligative properties. Alright, so colligative properties are pretty sweet. They've got a lot of practical applications. Okay, so colligative properties are defined as the properties of a solution that differ because you've put the solute in. Alright, now it doesn't matter. Now these are super interesting because it doesn't matter what solute you put in. It only matters how much solute you put in. Okay. There's three main colligative properties we're going to talk about. There's actually more, but these are the three we're going to focus on. We're going to focus on vapor pressure lowering, freezing point depression, and boiling point elevation. All right, those are the three main colligative properties. But first, let's talk about a little bit about a couple other things we need to keep in mind. All right, so this is just to remind you of what it looks like when we start dissolving things. So we got water, here's a salt cube, and remember the water surrounds the sodium and the chlorine, and remember it's called dissociation. Okay, now the Van Hoff factor is this factor that we have to consider when we talk about colligative properties. Okay, it's represented in mathematical equations as a lowercase I. Okay, for those of you in Algebra 2, I think, this is not the imaginary number square root of -1. It's a totally different I, so don't be scared. Okay, Van Hoff factor is I is just how many different particles one atom or one molecule will break up into when you put it in water. Okay, so sodium chloride, will break up into Na plus and Cl minus. Remember doing this? The sodium chloride will dissociate into those two things, and it makes two particles in solution. Ta-da! So the Van Hoff factor would be 2. Okay. Calcium chloride. All right. So this guy would break up into a calcium. Remember, calcium's got a 2 plus charge. Breaks into that, and then 2 chlorines. Yeah, because of that 2, it's going to make 2 chlorine anions. So we have 1, 2, 3. So we get 3 particles. So for calcium chloride, the Van Hoff factor is 3. Carbon dioxide is molecular. Remember that word, molecular? So it doesn't break up into anything. It just stays itself and just gets dissolved. So it's got a Van Hoff factor of 1 because it's exactly the same. There's only one piece over there. Cool, huh? Van Hoff factor. So this is just to give us a couple more practice problems. We've done this before in the past. Okay, so sodium phosphate. Remember, so we are this is our cation here. This is our anion here. So we're going to break up into 3 Na plus and 1 phosphide. So and phosphorus has a 3 minus charge. Okay, so its Van Hoff factor is 1, 2, 3, 4. So its Van Hoff factor is 4. Let's look at this potassium carbonate. Now remember, carbonate is a polyatomic. So this is our cation, and then this is our, this is our anion, and potassium is our cation. So we're going to get 2 K pluses, and then 1 carbonate. So CO3, 2 minus. Remember, you always have to look at that polyatomic ion chart. Remember, start getting used to that again. It's been a while since we looked at them. Okay, so we got potassium carbonate. So its Van Hoff factor is 3. All right, and then methane, well, this whole thing is molecular. It doesn't have any cation or anion in it. So it's just going to break up into CH4, just like that. And so its Van Hoff factor is 1. So which one of the following would affect a colligative property of a solution the most, assuming the same concentration of each? So pretty much what we're asking is which one has the highest Van Hoff factor. Well, sodium phosphide has a Van Hoff factor of 4, which is bigger than 3 and is also bigger than 1. So sodium phosphide has the biggest effect on the colligative properties of the solution. All right, so here's the 3 that we're talking about. Vapor pressure lowering. Now remember, vapor pressure happens when you have a closed container. Remember that? And you are having an equal rate of vaporization and condensation. Okay, this is from several weeks ago now. But anyway, so vaporization, condensation are at equal rates. So the vapor pressure, notice how this first one, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We've only got, 20 some odd molecules that are in the vapor phase. Okay, so we've got a fairly high vapor pressure of this substance here. Now, when we've added some non-volatile solution, so that means it's just non-reactive. Okay. So we've put something in our solution. Okay, this has disrupted their intermolecular forces, so it's harder for them to evaporate, okay, and easier for them to condense. So what happens is we'll get less amount up here in the vapor phase before we reach the point where they're at equal rates. Okay, so really what happens is we have fewer molecules in the vapor phase when we have vapor, when we have that equilibrium of vaporization and condensation. Okay, so notice here we've only got 12 molecules as opposed to the 20 some. Okay, so it lowers the vapor pressure when we add solute. Okay. All right, next one, freezing point depression. Now, when a substance freezes, the solid takes on the orderly pattern. Remember, we've got those molecules that are coming together, and they're going to form those intermolecular forces, and they form the crystal. We talked about this when we talked about phase changes. Okay, now if you put something in the way, it makes it harder for those molecules to make those pretty little crystals. Okay, this is really the essence of why a solute will interrupt and lower the vapor or freezing point. As our molecules come together and try to form bonds, the solute particles get in the way and disrupt them, so the molecules themselves have to get to a lower kinetic energy in order to make those crystalline patterns. Okay, so therefore, when we've dumped in solute into our solution, the freezing point of our solution is going to be lower than that of the pure substance. Okay, because those solute particles have gotten in the way. Now, the difference between those two things is called freezing point depression. Okay, so next unit we'll talk, or next part, we'll talk about how to calculate that actual value of how much lower that freezing point is. Okay, but so when you calculate it, remember that that's the difference. It's not the new freezing point. It's the how much it's changed. Okay, and again, it can't be understated that it doesn't matter what you've dissolved, it matters how many particles. Okay. So remember from chapter 15 notes, this is water, it's kind of all bounced around, they're really close together, and then it starts to make this crystalline pattern. Sticking a big old black sodium chloride in here is going to disrupt this ice crystal and make it harder for it to form that orderly pattern, so it has to get even colder. Okay, so if you add, this is just more of just talking about it, okay? If you add 1 mole of glucose to 1,000 grams of water, it lowers the freezing point this much, okay? So if you had 1 gram or 1,000 grams or 1 kilogram of water and you put in 1 mole of sugar, glucose, then instead of it having to get to 0 degrees before it starts freezing, you have to get it to negative 1.86 degrees before it starts freezing, okay? Adding 1 mole of sodium chloride to the same amount of water lowers the freezing point by this much. Okay. Now the big question is why? Well, it's really quite easy. Glucose is molecular. Its Van Hoff factor is 1. Okay. The Van Hoff factor of sodium chloride is 2, so therefore it's twice as effective. Sodium chloride is twice as effective, so it lowered its its freezing point depression twice as much, from negative 1.86 to negative 3.72. This is the essence of why we put salt on the roads when we're worried about ice, is because so we put the salt on the roads, and instead of us getting instead of us getting ice at 0 degrees Celsius or 32 degrees Fahrenheit, we can actually lower it so our water will freeze at 30 degrees. Instead of 32, or negative 1.1 and change, instead of 0 degrees Celsius. All we're really doing is we're saying, okay, sun, you don't have to get quite as hot in order for us to start getting the ice to melt. Okay. And then we can also put, like, this is also why we put antifreeze in our car and make sure that the water in our car doesn't freeze, because remember, when water freezes, it expands and you can crack your engine block. It's no good. All right, so we put antifreeze in there to make sure that when it gets super cold, that our water will not freeze. Okay. Boiling point elevation is very, very similar. Okay, only it's the opposite. You've raised the boiling point, so it has to get to a higher temperature in order to start boiling. Okay, it's all about making you're putting these solute particles in, so it's harder to get to the point where your kinetic energy can beat your intermolecular forces. Remember, boiling is all about making those vapor pressure equal the atmospheric pressure. Okay, so you've lowered the vapor pressure, so it's harder to get to the point where atmospheric pressure equals vapor pressure. So now boiling point is at a higher temperature. Okay, now this is going to blow your mind a little bit. You probably heard about how adding salt to your water when you're cooking noodles makes the noodles cook faster, right? Now, some people think that's because the water boils sooner. That's not true. What actually happens is that your water will boil at a higher temperature. Remember? So if you think about cooking noodles, noodles don't cook because because the water is boiling. The noodles are cooking because the water's hot. Okay? So by making the water hotter, you're making the noodles cook at a higher temperature, so they'll cook faster. Okay, adding salt to your water will actually make it take longer to get the water to boil. Okay, but it's going to be boiling at a higher temperature, so therefore it makes your pasta cook faster. Okay, so again, it depends on the number of particles, not the identity. Okay, putting sodium chloride in your water will make the boiling point go up twice as fast as dumping sugar in there. All right. All right, and that's colligative properties, okay? Not any math in this part. I just want you to get used to this stuff and do some practice. The practice where you're, thinking about these things, figuring out Hoff factors, okay, so on and so forth. All right, so do those practice problems and come take your checkpoint when you're ready.